Hello everybody and welcome to Handmade Heroes, show where we code a complete game live on stream. We are in the middle of, I guess I just want to say, fumbling around with some lighting in our game. The reason I say fumbling around is because we don't really have any particularly smart idea about how lighting should be done in sort of a 2.5D game. To the best of my knowledge, there isn't really a standard way to do it. And not a lot of people have really done that much with it, to be honest. One of the problems with 2.5D games in general is that the industry had kind of moved to 3D games, and a lot of the serious graphics programmers had all moved to 3D games. By the time the horsepower in PCs was good enough to do much in the way of interesting lighting, there were no such thing as, fully programmable shader GPUs back in the day when most serious graphics programmers wrote 2D games. So one of the problems with it is it's just not as developed as the theory of lighting in 3D games. And similarly, one of the problems with 2.5D games, of course, is that lighting kind of wants you to have a full 3D description of the scene in order to do it correctly. And even then, you've got a lot of questions you have to answer about how you're going to do it efficiently. And in 2D rendering, we really don't have that ability, right? We don't even know what the backs of things look like a lot of times. Some things don't even ever have a back drawn for them at all. Only characters who can actually face multiple directions even have sprites drawn for their various directions. So it's kind of a bizarre situation, and it's always a little bit of an artistic process, I guess I would say, to construct a lighting algorithm for something like a 2.5D game, because what you're really trying to do here is come up with something that approximates what light does in a way that's artistically satisfying, but that is knowingly incorrect pretty much everywhere because you don't even have the data you would need to do the job correctly. Now, we've had some success with this very process in a different domain, which is that actually all of the same things can be said for the fact that we wanted a 3D camera for a 2D game. And there is no right answer for that either, and I think we came up with a really pretty great solution. I love how our renderer works now. It's a fire and forget renderer, so you don't have to do any sprite sorting or anything. And it really looks nice when you move around, and when the camera moves around, I think it really captures kind of the motion and everything properly. So everything in the renderer came out exactly how I would want, and I think when we put the new art in, it's going to look really nice as well, and fix some of the other things. Remember, some of the stuff like the hero hopping, for example, which now looks kind of crappy, was done back when we didn't have real 3D, so it's not even really using the 3 dimensions the way it should. So I think stuff like that's going to look really nice as well once we go back and sort of do a final pass on things to get animation looking nice in the new 3D world. I think that's going to be great. But putting that aside, I'm really happy with how the renderer turned out, and I think it's very good for a 3D Zelda-ish kind of experience. I should say a 2D Zelda brought into 3D, which I don't know if Zelda really ever did all that effectively. There's definitely been some attempts at it. But, mostly Zelda went to real 3D for their 3D stuff. Anyway, so what I would like to do here is see if we can't sort of cheat the devil twice and come up with also a good, clean way of getting some nice lighting in here. Now, again, it doesn't have to be accurate. It just has to look nice. And already what you can see, I think, from me moving around with this light source attached to the hero, is that just very basic, simple lighting already looks pretty nice for a limited case. And so what I'm looking at here is just, can we extend this to something that gives a little bit more complexity to the lighting? So can we go ahead and make something that scales nicely to, say, hundreds of light sources, so there's a lot more lights in the scene than this one? Could we do something that adds perhaps a little bit of bounce lighting or other sorts of effects like that that will round out the feel a little bit more, make it a little bit softer, rather than being such a hard edge kind of a lighting? And the answer to whether we can do that is I have no idea. Like I said, it's a complete experimental situation. So where we left off last weekend is we were saying, well, maybe let's create some textures, let's write some lighting into the textures, and then let's try to use that lighting on the characters. And obviously the first thing that we can do for that is a very, very simple process where we could just take basic lights and write them into textures and just get the old school blobby, like this lighting doesn't even have directionality to it. Let's just get that working, right? Because that's hard enough to get working in GPU land, right? You can always have all sorts of weird GPU bugs that take a while to troubleshoot, and so it's not like if we were writing this code ourselves in our own rasterizer, it'd be like shooting fish in a barrel. But on the GPU, there's always a little bit of cross your fingers and roll the dice. So, what I want to do is just pop over, what day is today? 393. So to today's code, if you want to follow along at home, you want to use day 392 source code. That's the source code that I'm starting with. Let's open up 4Coder with the file names at the top. I added that back for everyone. People were complaining that I had switched it because now that 4Coder allows you to get rid of those bars at work, I don't use them because I always know what file I'm in, but people on the stream couldn't remember what file I was in. That makes sense if you're scrubbing around. It's probably hard on the stream. You scrub around and there's no file bar. You're like, what file's he in? I have no idea. So they're back. You know, they're back. I lost one whole line of code which, you know, I don't want to put that on you, but I did. And it's already like I barely get to see any lines of code because I have to have the font big enough for the 1080p stream. So it's like I'm looking at my code through this tiny little like peephole, like some kind of a like slit in a door or something, and I'm trying to look at the room on the other side. But anyway, so what we've got here is, I think before we finished on last week's stream, we did actually create this concept of light textures here. This is the OpenGL frame buffer sort of utility struct that we created before. And this allows us to basically say, all right, let's create a bunch of these light textures. I don't know how many, but you know, the game can decide how many and how big they are. And we said, well, we're never going to have more than 8 of these, so we just hard capped it there. But we probably won't be using all 8. I think we were saying we'd use 1 per color at the moment, so there'd only be actually 4, I believe is what our plan was. And what we want to do here is just say, like, okay, we want to write these lights into we want to write lights into these buffers, and then we want to go ahead and just kind of work out how the lights are going to affect stuff. Like, how will we look up into these light textures information related to the lighting? So there's 2 things we have to do here, and I'd like to start with the first part of that. So the first thing that I want to do is I want to upgrade the render group to allow us to put the lighting information into the scene. And let's talk about this a little bit here. Because effectively, you know, we've got a depth peel renderer, right? Oh, and this reminds me of something that I thought of during the week. I had a random thought about this that I don't know if it's particularly useful, but it might be, and we'll have to think about it. All right. So effectively what I want to do here is break lighting down into something that's a little bit more manageable. So let's think about this. What's the easiest thing that we could possibly do if we wanted to capture lighting and use it like we are currently using it, right? So let's suppose I've got my 3D world here, and I'm going to draw it from the top looking into it, right? So here are the various floors, and maybe, you know, like in our case, we have a hole in the floor so you can see down to some stuff, right? So, you know, you can see potentially multiple layers, even though like right here might be blocked because this is opaque. Here might be, you know, you can be able to see through it, right? Okay. Now, if we were in 2D, so this was looking top down, and I'm looking at the actual game. If we were in 2D, you could imagine making like a grid, right? And you could imagine our light sources could be put into the grid in such a way so that if there was a light source that was in a particular grid, we would record the information about that light source, right? Like suppose we were talking about GPU at all, we could just do the same thing we're storing right now, which is like a P and an I, like a position and an intensity. I think we called it strength. So P and an S, but intensity of the light source, right? So this is where the light source is, this is how bright it is, and we just have a simple point source model. Like we're not trying to model area light sources or anything like that. We're just doing points, and we figure if we want areas, we'll just add more points or something like this. Right? So the first problem we run into, right, is when we try to map this into hardware, we have a fixed storage size. And there's ways you can get around fixed storage size, but it becomes increasingly more complicated. So we've got a problem where we have a grid, but it can only store, for example, one of these. So if we have lots of lights that are overlapping in here, we need a way to merge them, right? But that's not the end of the world. You could imagine merging the position and source of the light fairly straightforward, right? We could imagine just averaging the position of the light source, let's say, and averaging the and summing the strength of the light source, and that would give us, if we did that for red, green, and blue, that would give us an interesting approximation to the light. Is it something that's good enough? I have no idea. We haven't tried it yet. Okay, so I feel like this is the first thing I want to get working, just something real basic like that. Let me quickly mention the other thing I was thinking about just separately, but this is the first thing I want to get working. What we have to do here is introduce a light accumulation pass, right? Where basically before we render any of our depth fields, we want to first render all of our light sources, just the light sources, into some kind of a set of textures. We've got those textures now, we'll render into them. Right now we'll just stick with 2D. When we get 2D working to our satisfaction, we'll make those textures 3D and see if we can get that working to our satisfaction, right? And we can go from there. All right, so here's the other thing that I wanted to mention that I thought was pretty interesting, and we'll see what you folks think of it as well. So let's suppose I wanted to do something like this light source rendering, right? But I wanted my light to more accurately reflect the geometry. So for example, let's suppose that I go into here, right? And I'm hopping around, right? And the light's moving, but one thing you'll notice about the way the light's moving is there's no shadowing at all, right? And that is actually true pretty much everywhere. So for example, because all we're doing is a radial light, right? We haven't done any real work on this lighting. So what that means is you can kind of see, for example, as I move around, this surface gets brighter or darker based on how far I am from the light, or like say the underside of this surface, but that light would never be able to hit those, right? Even bounce lighting would never really illuminate these underside surfaces, because by the time the light bounced off the side of one of these, off the bottom of the top of one of these, and up onto here, it would be incredibly dim, because a lot of that light would have gotten absorbed. You know what I'm saying? So right now we're strictly doing radial fall off of the light, and that's not very compelling. It would be nicer if we took into account some of the geometry there in terms of shadowing and occlusion. Now, one way that you can do that, obviously, is by using what are called shadow maps, and that's rendering things from the perspective of a light source in order to figure out where the shadow is. It's very good for things like single light sources that cast strong shadows. An example of that is stuff like the sun. When you're doing something like lighting from the sun, a strong directional light source that casts very strong shadows, and you want something realistic, a shadow map makes a lot of sense. When you are casting from hundreds of lights, it makes a lot less, right? And to the best of my knowledge, I don't really know if this is true, but I think it's true. Even modern, very advanced renderers that require high-end hardware, like Doom, the new Doom, not the old Doom, those games put a lot of limits on how much they do with shadow maps. So for example, in Doom, I think they're updated somewhat lazily. So basically what happens with shadow map lighting is they basically try to limit how much shadow map rendering they do, and they cache them from frame to frame and only update them when they have to try and get more out of them, like, because again, they're expensive, right? And so I don't really know of games that do all of their lighting with shadow maps in that way. I don't know how feasible that would be for games that aren't just a few light sources. Something like Doom 3 is an example of something that could easily be done that way, but of course that didn't use shadow maps. That used shadow volumes, which is a whole another ball of wax, and not a technique that anyone uses anymore as far as I know, because it's extraordinarily expensive, just very, very expensive. So anyway, yeah, so I'm not sure that shadow maps are really our answer here, especially when you consider the fact that we don't have real geometry. It makes it very hard probably to eliminate the artifacting that would happen on shadow maps, so I don't really want to go down a shadow map route. I think that would be a real bad idea. That's just my guess. I don't know, but I think that would be a pretty bad idea. So what I want to do instead is think about other options for kind of getting a little bit of that back. Again, I'm not really, excuse me, I'm not really looking for a lot of direct shadow effects anyway. I don't really want like long sun shadows or anything like that. I don't really want the look of that the game to be like that. I want soft, very soft shadowing. So what I'm really looking for is something a little bit more diffuse. And anyway, what I was thinking, I realized this just during the week while I was kind of randomly, I don't know, my brain must have been wandering, and I was thinking about this. So what happens when we render our game right now is we produce the top level pixels, whatever those are, right? In our first depth peel pass, right? So this right here is depth peel 1. We end up with a Z buffer that looks like this, and this is depth peel 1. We then do another depth peel, right? And we end up with a second layer of the scene, and so on and so forth. So we end up with multiple layers of our scene in our depth peels. What that means is we actually have some very interesting information that a normal game doesn't have. So, for example, we could tell you if a light source was here, we could tell you that it was going to hit something down here. We've got that information in our depth peels, right? Which is pretty interesting. So one thing that I was wondering is, I wonder if we could do something where we use our depth peels as the geometry for some bounce lighting. It's a long shot, but it seems plausible, right? Because one thing that a lot of people do already is there's a lot of screen space techniques, right? You'll see things like SSAO talked about, which is screen space ambient occlusion. And what those techniques do is they're just techniques which use the depth buffer to approximate some kind of lighting effect. So screen space ambient occlusion, for example, is a technique that takes a look at depth buffer things, and where it sees things where it looks maybe something like that in the depth buffer, where it sees an inscuse area, it will assume that less of the incident lighting can hit this area and it'll darken it, right? So it's kind of like a filter that you use over local areas of the depth buffer that try to determine whether it looks like shadowing will occur in this area in a generic sort of inbound light sense. And to the extent that you want to spend more pixel shader or fragment shader time on it, you can get better or worse results by doing more work, right? You can look at look at more areas of the depth buffer. You can do it per light. You can do all sorts of things, right? So that's an example of a technique that sort of works exactly the way that I'm describing, just not with multiple depth peels. So if we have multiple depth peels, it seems like we have an even more powerful opportunity to potentially do something involving convecting some of that light around. Now, I don't know if that's really true. It was just a little bit of a thought, right? And so what I figured we would be able to do in certain circumstances is potentially have, instead of voxelizing our scene, which is not necessarily something we want to do due to the added expense, we're already depth peeling it for our render. That kind of gives us an interval version of a voxelization of the scene. Because for every pixel on the screen, we effectively have the voxel in Z of that pixel, right? We've got specifically the empty space to the first filled space. We then have the empty space to the next filled space, the empty space, and so on. Now, we don't count backwards faces. So we don't really look at this part of the voxelization, but since most of our objects are thin, I'm not sure we really care about that. We may be able to get away without that. And if we really needed it, we could add that as part of our depth peel pass. For doubling the cost of our depth peels only in Z, we would not have to render any pixels, remember. We could do an alternating depth pass every other time just to write an additional Z buffer that was the outbound Z there. And then we would know this. So even that is not an impossibility. We could get back that information if we so desired. And so I think what I'm trying to get at here is we sort of have a voxelization of our surface already. Whether that voxelization is any good, I don't know. Like whether it's useful to us at all, I have no idea. But it's something, right? And so what we could consider doing here, rather than the light textures being used the way that they're currently being used, is we could imagine, again, looking out at sort of a more voxel cone tracing sort of a thing that actually was a little bit more light tracy. I don't know that that's a particularly good idea, but it's one way we could take a look at this problem. And I'll bring something else to your attention here, I guess, while I'm going down this particular rat hole. Trying to remember the search terms for this. Graphics, gems. Is this what it was? This is not it at all. Nope. Really wish I could remember what the name of this was. So there was a technique that was used for radiosity that I cannot remember. Arg. There was a technique that was used. There was going to be a game based around it, but it never materialized. So I don't really remember. Let's see here. GPU Gems, Pirates of the Caribbean. I know this is a really weird way to search for this, but this is it's the technique that they used in Pirates of the Caribbean that they got out of GPU Gems. But they, of course, don't specify what it was. I'm going to find this. This is just some pirate site. I don't want pirate stuff. I want Pirates of the Caribbean. Which GPU Gems was that? If someone could just tell me what that was, it would be nice. Does anyone on the stream know? That's it. Fantasy Lab. So this is what we're looking for right here. So this is what I was thinking of. Finally found it. That took a long time. But basically it's an iterative scene, an iterative scheme that kind of like convex light around your scene, right? And the way that this thing works is that you create individual points and you kind of bounce them around, right? So let's see here. This is not the actual paper I'm thinking of, because it's the GPU Gems one that I'm thinking of. I give up. I can try and find it offline. But basically, these are just, it's a pretty straightforward idea, right? It's not particularly bizarre or anything. I would like to show you the shader, and it was in GPU Gems, but unfortunately, is it in here? Here it is. Okay. Finally. I finally found it. Man, that was a long dive. My memory knew it was there, but it couldn't remember enough to find it. Okay. So basically, here's how this thing works. Just to refresh my own memory. The idea is that you have these little splatty things, right? And the idea is you've got a disk that's pointing in a direction and has a radius and a color, a lighting value, right? And what you end up doing is you take these things and you do passes to scatter light around them, right? So it uses a approximate equation to figure out how much light is transferred between two different receivers, right? Like so. And the way that it works is it says like, all right, here's the algorithm description. We calculate the accessibility value of two passes. First pass, we approximate the accessibility for each element by summing the fraction of the hemisphere subtended by every other element and subtracting the result from 1, right? So that's basically like looking at, it's sort of like an n-squared thing. After the first pass, some elements will generally be too dark because other elements that are in shadow are themselves casting shadows. So we use the second pass to do the same calculation, but this time we multiply each form factor by the emitter element's accessibility from the last pass. So basically they do two passes to try and do shadowing and remove things that are doubly shadowed, right? So that they don't double shadow, if that makes sense. So this doesn't really help with lots of shadowing. So if you have tons of shadowing, you need more passes. But, you know, again, this is a hacky approximate lighting technique. So after figuring that out, let's see here. Here we go. A single bounce of indirect light using a slight variation of the ambient occlusion shader. We replace the solid angle function with a disk-to-disk radiance transfer function. We use one pass of the shader to transfer the reflected light of emitted light and two passes to shadow the light, right? For indirect lighting, we first need to calculate the amount of light to reflect off the front face of each surface element. If the reflected light comes from environment lighting, then we compute the ambient occlusion map, blah, 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 right? Now, what they do here, because this gets way too expensive, is they just do these things hierarchically. So what they do is you have all these little surface occluders like this, right? You have these little, like, sort of approximate blobs. What they do is they say, well, okay, these approximate blobs, we can just, for ones that are further away, we'll just merge them into something that's less resolution, right? So really that's all they do to cut down on the amount of work. So when you consider, you still do an n-squared, you still do n-squared work versus the other occluders. You just make sure that n-squared never grows particularly large, because you always, as you look at occluders that are further away from you, you always look sort of at a more coarse version of those occluders, right? So I think that's about it. Let me see here. Yeah, here's the hierarchical elements thing. So basically what they say is like, you know, we need to improve our algorithm to work on more than a couple thousand elements in real time. They use simplified geometry for distant surfaces. So what they do, we group elements whose vertices are neighbors in the original mesh and represent them with a single larger element. We do the same thing with the larger elements, creating fewer and even larger elements, forming a hierarchy. Now, instead of traversing every single element for each pixel, we traverse a hierarchy of elements. If the receiver element is far enough away from the emitter, say 4 times the radius, we use it for calculation. Only if the receiver is close do we traverse its children, if it has any, right? So again, just a really simple technique of sort of grouping these light sources up together in solving for only simple ones, right? So that's, I mean, again, I feel like that's the sort of thing that we could really, if we wanted to, we could play with here. Because I guess I don't really know exactly how we would do one with the depth peels. But if you think about it, when we create these depth peels, at any particular point, when we write the depth buffer out, we could also write out the normal. So we would know where the surfaces were and which directions they were pointing, right? Which would give us a set of bitmaps that actually had what we would need for bouncing light around from just the depth peels. Once we had that information from the depth peels, excuse me. Once we have that information from the depth peels, we would then be able to say, well, okay, let's filter those down. So we've got 1920 by 1080 versions of this data, which is way more than we want to work on. Let's just filter it down. So then we would do, you know, a version of this that was like half down and then half down again and then half down again, right? And each, as we would do it, we would just successively sort of approximate those other values, which are full resolution. In this case, we would approximate those by like summing them together, right? And furthermore, we would know what size those things were because they would always be proportional to whatever the bitmap was we were sampling out of. So we could do something like that where we just say like, okay, as we look for things that are further away, we just look at coarser and coarser approximations of those things. I don't know. It could work. It could also be an absolutely terrible idea. I have no idea. But, you know, again, that's kind of just one way we could play around with that lighting information. And it feels like something somewhat useful. And for our purposes, what I think I would do, since a lot of our stuff is flat stand-up sprites, I would just consider everything to be two-sided. Right? So when we do the equations for the lighting transfer, I would consider everything to be two-sided, and I'd just track both sides. So when we process it, I'd store, like we'd have double the storage for RGB, which, you know, each side of the surface would record it. So I don't know. I mean, this may be just really stupid. I have no idea. It's just kind of tempting, and I feel like I want to try it. And again, mostly what this would require is just, it would require the directional, saving that directional element, what direction the thing was pointing in. Right? And I don't think there's really much else to it. I think that's basically all there is. So yeah, so basically what the expense becomes there is it's really a bandwidth expense, is the primary thing in the depth peel. We're not doing any more work in the depth peel, we just have to write a little bit extra, and that writing a little bit extra is costly, right? Because now we need to write out a normal, which is 3 elements. We can cut that down to 2 by not writing the third, because we know from Pythagorean theorem that if we're just storing a direction, we can just store the x and y, and we can always produce the z by renormalizing, right? So that's pretty straightforward. And I think that's really all we would have to do. So what we could do here is say, yeah, we could introduce an additional RGBA texture in here, perhaps. Although I guess that's not that useful now I think about it, but yeah, so if we have the R and the G, That would store us our direction. Unfortunately, we don't have enough information here for the light. Well, oh, you know what we do? We know that the color is whatever the color is in the actual bitmap, because we have an RGBA, which here is the alpha, and here's the color of that thing. And so in theory, I guess, we could just store the two, like an intensity of each side. The problem with that is we wouldn't be able to bounce colored light around the way we want to. So really what we probably need, again, is two of these, right? So we would store something like RGB of the backside, RGB of the front side in terms of the bounce state. And then this A here this one and this one would form our X and our Y, right? They would not be alpha values. They're the X and the Y of the directional normal of whatever we rendered at that surface. I don't know. I have no idea. This could be a fantastically stupid idea. I really just do not have any idea whatsoever about it. So if we did something like this, then what you can imagine is in order to start bouncing the lighting around, what we would do is we would, for any given one of these elements when we go to render, we would probably do something where we just sampled from the bitmap a couple times. So we would sample from the bitmap that was like right in the region of this thing. We'd sample from a high-res version of the bitmap. Then for everything out here, we'd sample from the lower res, and for everything out here, we'd sample for a lower res again, right? The problem with doing it this way rather than doing the splat way is, again, that it doesn't really capture the geometry hierarchy quite the way that they were capturing the geometry hierarchy, but I don't know, it might still work out okay. And this gets us out of the volume texture business, so there's no volume textures in here whatsoever, which is another pretty nice aspect of it, right? It's entirely screen space. So I don't know, that sounds kind of fun, so I think I might just try it. We may be on too old a hardware to really get this to run in a reasonable amount of time, but it's been long overdue for me to move to a modern card. So what I probably should do one of these days is just replace the Handmade Hero machine with something that has a modern GPU in it. And we'll have to do that sometime soon regardless. So yeah, what I would say here is we need some argument about how we're going to do the sampling, but other than that, I think we're pretty much fine. Because if we just have a reasonable rule for sampling out of those textures, we can just use exactly this transference that they're using here. We could just use, and then we'd be fine, right? And I think that should just be about it. This here, where instead of ever having an emitter area, we would just know the emitter area would be proportional to the bitmap resolution that you were at, because it gets successively filtered down. So basically what would happen here is just a lot of texture reads. For every one of these, when we do the lighting, it would need to read from, basically, for each depth peel, it would have to read from 3 textures, right? And it would sample from those textures at different MIP resolutions as well. So it would sample from, each successive MIP level, it would have to sample from. I also think that would be a problem with introducing lighting discontinuities, because if you think of what will happen with the MIPs, right? The MIP levels do things like this, right? So let's say we're computing the light from right here, and we wanted to sample, this area. We're going to have this problem where we introduce a discontinuity because someone who is sampling the lighting from just slightly to this side would then not sample like these. So right across that boundary where you go to a place where you wouldn't maybe where you wouldn't be in the right place in the MIP maps, I wonder if that's a problem. I guess what you could say is, well, at the higher levels, at the coarsest levels of the MIP map, we just sample everything, right? So everybody gets lighting from the 4 most coarse versions or something like this. But then as you go down, you get, progressively more refined. I don't know. It seems a little iffy. It would be nice to be able to do something more like they do it, where they've got those hierarchical vertices. The problem with that is I'm not sure how we would really get this hierarchical vertex structure I'm not sure how we would really produce that. I'm not sure how we would do sort of that clumping. So here's a thought for you, and I'm really just, we are out in complete la la land, and I admit that, but it's lighting. What do you want from me? Here's another thought. What if we did this in a multi-grid fashion? So what if we said, okay, here's what we're going to do. We splat all this stuff out using the depth peels. We then filter it down so we now have, a proper MIP map pyramid like this, where we start out with a 1x1, and we go down to a 2x2 and a 4x4 and an 8x8 and a 16x16 and so on. What if we did the lighting on the pyramid? So we have these splats that get successively more approximated. When we get to the top, we just have one lighting element, right? So what if we did an up-down kind of version of this thing? So we start out, we've got all these pixels. As they filter up, the lighting, anything that's an emitter, is obviously getting written into these successively more filtered versions, right? So as we go up this tree, we do a bounce, like we do transference. The 1x1 really doesn't have any transference. So we start with a 2x2. We do the transference on the 2x2 to take whatever their average illuminations are and average directions, and we bounce the light once there. Then we go down the next level to the 4x4, and we push the lighting from the 2x2 down to the 4x4. So whatever light got added at the 2x2 gets added to the sub-elements of the 4x4. Then we take those and we bounce the light again, writing it into the 8x8, right? Then we take the 8x8, we bounce those, and we write it into the 16x16. This sounds fantastically stupid, I admit that. I don't know that there's any reason to think that this is going to give anything like good lighting. I also have no idea how we would ever debug it if it were not giving good lighting, and we wanted to make sure that the reason it was not giving good lighting is because the idea is stupid and not because the implementation has a bug. So that's a little bit of a problem, admittedly. However, it has one nice element of it, pun intended, which is that it operates in a very consistent time fashion. So you get this sort of, you know, successively coarser approximation. So if you want to, for bouncing the light around really far, you do it on the 2x2, and it propagates downward and downward and downward, you know. So yeah, I could believe that would work to do something resembling something. And so you keep following this process down, right? You write it into the 32, the 64, the 128, the 256, the 512, the 1024. And the 1024 is maybe how far we go, right? So we just have like a 1024 by 512 or something that we write these splats into. I don't know, and then that filtering process occurs. And by the time you get to here, you end up with this is your light value that you would actually apply to the things in that area. And the light value tells you what direction it's coming from, roughly, let's say, because you've got that bouncing. So yeah, I mean, if I was just to pretend, let's say in my head, that I believed for a second this was going to work, which I don't know that I do. But basically what you do is you do surfaces up, right? And you do directions down. So you take your depth fields, and right now let's just do the top depth field, because we don't really need to worry about volumes if we can't even get this working for just the surface, the very top one. So you take your depth field. You assume that you stored the normal to the surface at that point that you were rendering out. You write those into some lower res version of the bitmap. So the 1024 by 512, let's say, by just taking samples. You don't even have to average necessarily. Let's just take samples. But we could average if we wanted to. We could take the 1920 by 1080 and we could sample, you know, and do a smooth interpolation of those values, right? So we could bilinearly filter from a 1920 by 1080 to get the 1024 by 512. So we do that. We now have the proper, or you know what we could even do? We could even just do this. I guess we don't really even need to do that. We could just do the 1920 by 1080. We could just subsample that. So we could say it's always just a divide by 2 of the thing. Who cares about the wasted space, right? We can just subsample each individual version of that down further. So, okay, pretend we do that, let's say. So we basically have the 1920 by 1080, and then we would have a half version of that and a half version of that going down as far as we wanted to go. So we take those, we produce the surfaces, and those surfaces are just just a direction vector of the direction the surface is pointing, and the color value, right? Of the light at that point, which for most of the surfaces is going to be nothing, and for emitters, it's going to be the emitted light value, right? So we successively average those going up to produce average surface directions, and we average the emission going up as well, right? We then, and I guess now that I think about it, it's the same. So surfaces up, directions down is really the same thing, because the surfaces are the emitters as well, so the directions are always just going to be the direction the light's going in, right? Okay. So then we have at the top, we've just got one value that's like the overall average emission of the whole scene. And the overall average normal, which doesn't really give us much information at all. So we don't care about that at all. But then the 2x2 down, it's slightly better, but not really, right? It's not that much information. But nonetheless, we do the whole algorithm. So then we do the shadowing and emission on that. And what we basically produce there is the delta value of how much shadow, how much emission we produced, right? So at this level, in each of the cells, it's a 2x2. We've got, in addition to the direction, which we're not going to change, we've got the average direction. We just have the, the plus or minus RGB, right, for each of these cells. So after doing the lighting calculation, how much did each one get brighter versus how much did each one get darker? So we take that plus or minus RGB, right, and we add that to the next level down. So in this case, now we've got for each of these cells, let's say this cell, we have 4 cells in the bitmap below us. So we take whatever that plus or minus RGB was and we add it to each of these 4 cells, right? Then we do the exact same thing on these 4 cells. So these 4 cells themselves now do the same shadow transference that we do here. So it's just every time it's just on a set of 4 cells doing the transference on 4 cells, right? 4 cells, 4 cells, 4 cells, 4 cells. So I don't know. Would this do anything resembling anything? I have no idea. Probably not. It's probably just stupid. But that's my stupid idea. I hope you like it. So I think that sort of works. What I don't know is how much discontinuity that introduces because of the bitmap boundaries. My fear is the answer is quite a bit. And so then what you'd end up with, I fear, is that you'd end up with some hard discontinuities in the lighting. But I don't know, maybe that could be mitigated by just when you finally go when you're doing this push down, maybe you add a little bit to the neighboring one to like help smooth it out. I don't know. But that's my fear. My fear is that you end up with these hard edges in the lighting because at the screen was at its coarsest level divided into 4 sections. And I fear that like this whole section of the screen is going to be slightly brighter. Now what we could do there, again, is we could just kind of bloom filter that out a little bit, like blossom it out to smooth it. So when we do that sort of plus that delta RGB blossom, when we're going to process the lower down versions, we could add that out to the neighbors at a linearly interpolated amount. And that would probably solve that problem. But it may just be, I don't know, it may just be intractable. So I don't know, this is a really ridiculous idea, but I kind of like it. And I kind of want to try it. And the depth peels were kind of a ridiculous idea. Alpha blending through depth peels is not something that I ever heard of for a 2D game, but it worked great. So sometimes in game development, you just want to press your luck. You just want to press it. Because the last thing you want to do is not press your luck and have you miss out on something lucky. It's only time that you're wasting, right? You don't have to stick with the routine. If it turns out to not work, we throw it out and we do something else. So since I kind of like this flavor of hierarchically merging, I kind of feel like that's what I want to do. And I feel like I can do that fairly easily. To be honest, on the pass upward, I don't even know if we need anything other than just a simple bitmap filter. Right? Because on the pass upward, all we would really need to do is we're just blending directions and intensities. That's it. So yeah, I mean, I think this is going to be pretty straightforward. Yeah, I don't know. I mean, it seems pretty straightforward. Now, we do have, I guess that, yeah, again, the problem is just these are very big textures, because now I think about it too, because we're talking about this being a depth peel rather than a voxelization, these things also have a position, right? And really, technically, if we want to do the whole thing, it would be 4. We do all 4 depth peels probably at once. So we'd be talking about just a really huge, so we'd have a 1920 by 1080, right? That's 4 depth peels is what we're doing at the moment. That would go, and that's by 4 elements as well, right? Or by several, I guess we're not going to talk about that one because that's our color. We also have the depth buffer and all that sort of stuff. But anyway, so we have 4 of these things that now will come through. We need, I guess we don't need to know, now that I think about it, we don't need to store the XYZ position of the emitter because that's always given. We just need the depth of the emitter because since we know what pixel it's on, we know where it is along a ray. We just need to know how far along that ray, right? So reconstructing the 3D position is not particularly difficult because the depth gives us that information. So really we don't need that. We've got these, so all we need to store is we need to store the depth, 2 RGBs for the color intensities of the back and front side of these surfaces, of the emitters, and the direction, right? So this is 1 element, this is 6 elements, this is 3 elements, right? So total-wise, we've got 10 elements there, if I'm doing that math correctly. So depth, 2 colors, and a direction. Now, like I was saying, probably we can eliminate one of those and get it down to 2. So it would be 9 elements. And then there's the question of if we want to do one for each depth peel. If we did it, would be 4 times 9, or 36 elements. Since 9 elements is really 3 RGBA textures, I'm sorry, 3 RGB textures, you could think of this as 12 textures. 12 RGB textures, right? Or we could think of it, if we had them be RGBA instead, we would end up with 9. And we'd have to pack them creatively, right? I think I would go with this method first because this is an optimization and this at least keeps things stored in a sane sense, right? So it keeps basically 1 RGB emission front side, 1 RGB emission back side, front, back, and then 1 RGB 1 XY plus D for the depth and the XY of the direction. Right, so 3 textures per depth peel to do the lighting, right? And then each one of these, so you've got basically this really big bulky process here. That's all the time. So you've got 12 texture filter, that goes down, down, down. It's got to it's got to read from 12 textures, produce the result. So that's going to be a really meaty, expensive process, right? As it does that big deal. Once it's done, however, I think then that's it. Lighting is now super straightforward, because now all you're going to do for lighting is you're just going to look up like the closest thing. So you're just going to look into that that final texture, whatever that is, the 1920 by 1080 texture. You're just going to look into that at your pixel location. You're going to pull out the lighting direction and intensity. You're going to do the calculation. Or actually, you're not even going to do that. You're just going to pull out the intensity and use it. That's it. Because you've already gotten down to just you. You're on yourself, so you know what your lighting was. That's it. You're done. So the lighting is just here. I don't think there's anything else to it than that, right? Yeah. So I think that's one. I think that's roughly correct. The only thing that's, I guess, to be honest, there is one more kind of thing to that that's not, so that's not quite true. I think we actually have a slightly worse situation for the textures. I think it's probably more like 4 textures here, because I feel like we'd also have to do the RGB reflection. Or I should say, like, what the surface reflectance is. So this is like the surface parameter, because without that information, we wouldn't know how incident light on this, on whatever this element is, how it bounces off, right? So we would know the light coming in, but we wouldn't know how the light bounced off. And so when we kind of average those up, we would need to record both the reflectance and the emission values for this surface. So how much light is it giving off right now versus how much, when we get new light in, how should that light be modified in this case, right? So it seems like it's really more like a 16 texture filter, right? And again, so that's really heavyweight, and that's unfortunate, but you know, I don't know. That's just how it goes, my dude. Oops. Yeah, so I think, I mean, if it's a 16 texture filter, the problem with that, I don't really think it's that expensive is the thing, because you're only doing it once for the whole screen. And you're doing it on, you know, the bitmaps. I think most modern cards would not have any real concern about that. My only thing that I think would be a problem here is that cards that can't do 16 taps are in trouble. 16 taps is the wrong word. Sampling from textures, they can probably sample from textures a lot. The problem is how many textures you're sampling from. And so 16 textures is probably just a lot of textures, like too many textures. So that's a little bit of a concern, right? And I don't know how to get around that particular problem. I feel like it's definitely an issue. So that's a little bit of a problem. The other thing that's a little bit nasty is I don't think the cards like support multiple render targets. Modern cards all do. I don't know if like cards as old as this one would support multiple render targets. And the reason that that matters at all is just because we need to be able to store the direction components. Right now we just store RGBA depth, which every card can do. We would need to store RGBA depth normal, which requires writing to a second color target because it's going to have to store that X and the Y value, right? So yeah, so that's pretty bad. Again, for a modern graphics card, that's nothing. They would not care about that at all. It's pretty milquetoast. For this graphics card, I'm just guessing that it would be a complete disaster, right? Now, the render target part we could fix. The render target part is easily fixable. So what we could do is implement our renderer, and in fact, we probably do want to do this. Now that I think about it, we could just get the approximate normal by using the by just doing another pass that records what the normal was at the closest point for that depth pass, for that depth peel, right? So just after we do it, we do one extra pass to write the normal. That would not require writing to an extra texture. So that'd be pretty straightforward, I think. So I'm not too scared about that. The thing that I am scared about is the 16 source textures. So let's find out whether that would even be possible on this machine. OpenGL parameter for maximum textures, maximum samplers. GLSL maximum number of samplers. So 32 samplers would be well more than enough. That would be twice the number we would actually need if that was the limit. But I don't know if there's a good place to look at that. What is that site that does OpenGL graphics card capabilities list? All right, so let's take a look. So this is whether or not we would get an extra render target, right? So it looks like mostly everything allows 4 color targets, though, or more. Unless that means 4 color... I mean, I guess max color attachments, we could just query on our card, and that's probably the floor. Max color attachments is just whether or not we could write out the other bits there. Excuse me. And that's the maximum of color attachment points in a frame buffer object. I just don't know whether that means color channels. So if RGBA means 4, then that's one thing. If RGBA means 1, that's another thing. So I would like to know what the definition of that actually is. in the spec. So I'm going to look. May range from 0 to the value of max. So, okay, so 4 means you could write to 4 render targets at once, even if there are GBA, according to this. So that means writing out the direction should not be a problem, even on a card as old as this one. We can query it and find out, which let's just do that. Do we have an info? Here it is. So in our OpenGL info, let's do, in here, we'll just do, although you know what, now that I think about it, the way we actually were doing this is we were doing it in here more. So maybe I'll just put them in here for now. So max color attachments, max samplers, shader. So let's get those values. And just see what they are, because I'm curious to know. And again, this is an extremely old card, so if it worked on here, it's probably totally fine for backwards compatibility, because this card is ancient. Looks like we're not doing a GL get param I anymore anywhere. Oh, get integer. There we go. So we are. I was going to say, I thought we were getting one specifically for that. Okay, so let's do color attachments. And then we also need max sampler or something. Max. We need something that tells us the samplers. So the OpenGL running context is multi-independent bind location for textures called texture image unit, blah, 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 blah. Okay, so the concept GL max combined texture image units. That is what we would need to know. So I think those are the two values, and we'll probably have to get those because those are extended values. So we'll have to get those from CoreR because those are not in base OpenGL, since base OpenGL didn't have any of those. Max color attachments. And max combined texture image units. And let's just see what these are, because I have no idea what they are on this card. So this should be GL ints. And so if I take a look at what those work out to be, so yeah, I mean, it looks like we could just do this. Even on this extremely old card, it seems fine. Let's take a look at what this value is on something like an Intel integrated graphics part, which tend to be the worst for texturing. Let's just see if we can get a little visibility into that. So my goodness, that is a large value. So here's a page with everybody. Looks like they're sorted from least to greatest. So even back really old, it looks like they were okay with 16. So we would be right at the limit, but we would be functional. The only thing I don't know is, do the number of color attachments that you have, does that affect that? So if you have one color attachment, does that cut into your texture unit? I assume texture units are only for sampling textures in this description and not the frame buffer out, because the frame buffer out's a very different path that doesn't have a lot to do with texture sampling. But if there was a question of address registers where like you only have this many texture addresses at all, then the texture to which you were rendering would count. So that's a question. But the good news even in that case is by the time you get to anything even reasonably modern, you're up to 32, it looks like. So I say let's do this. I mean, it's dumb, yes, but you know, dumber things have worked, you know? So let's try it. Okay, so if we're going to do this, then what we really need here is we no longer really have the concept of a light texture in this sense, right? It's not quite what we would be creating here. What we have instead is something where we're going to store this extra data in a mip-map fashion. Now, I don't know that we actually need to have these things be mip maps, because we're never sampling from them as actual mip maps. So really what we want to do is take this notion of the light mip count, and then the light mip count is going to give us how many of these light textures we need. And the light textures are just going to be successively downsampled versions of our 1920 by 1080 or whatever it is, right? So assuming that we start at 1920 by 1080, how many times would we have to downsample it, right? And so, you know, if I take 1920 and I divide it by 2 and divide it by 2, right, this is the process that we're going to be doing to get down to the minimum level that we want, right? Whatever that minimum level is. So if it's 1920 by 1080, what you can see here is at some point, unfortunately, we get down to 15, and there's nothing we can do below 15, right? Anything that we do below 15 will sort of unevenly sample, which we may not want to actually do. So we're really looking at something that's like 15, and then 1080 has the same problem, obviously, right? As you divide by 2, you get, in fact, that's pretty soon, right? You get down there. So I don't know how we want to address that problem exactly. There's a couple of different ways we can do it. One is we can start with 1920 by 1080, and just when we get down to that level, just let ourselves do a sloppy sample, right? So let it be the fact that, yeah, you don't accurately do down by 2 at this point. it's actually going to sample from, it's going to bilinearly sample or something, right? So we could totally do that. The other thing we can do is start with something that's not 1920 by 1080. Start with something that's actually 2048 by 2048 and sample that down, right? And just do the upper corner of it as it gets sampled down and down and down, right? Again, that doesn't really help us because the same thing's going to happen to the sub-rectangle there. So I think probably what we want to do here is we just want to take, these textures and I think we just want to go ahead and do their successive versions. Now, there might be some win to doing the larger bitmap and having it so we're only having to access its LODs. And that win would come if we ever tried to read from more than one LOD at a particular time, right? But I just don't know if that's something that we would actually be doing. It doesn't seem like something we would be doing. I mean, the basic description of the algorithm that I outlined before certainly doesn't do it, because you're always reading from one level of the MIP chain and writing to another level of the MIP chain at every step in the process. So at no time do you actually get a benefit where you are reading and or writing from multiple levels of the MIP chain. Well, writing the levels of the MIP chain is a separate issue. At no time are you reading from multiple levels of the MIP chain, meaning you never read from the MIP chain like one level up and the level that you're currently on. And furthermore, you couldn't do that because if you were going to do that, you would be writing to the same texture you were reading from, which is generally not allowed because the sequencing breaks, right? So it seems to me, I mean, just sort of closing my eyes and imagining it, it seems to me that you could get away with just these always being two separate texture handles and off you go, I think. So anyway, if I have a 1080 texture, well, a 1024 is 2 to the 10th, right? So if I do 2 to the 10th, I get 1024. So I'm suspecting that I will need 10 MIP levels, roughly. Now 1920, right, if I was to take and do that 10 times, right, so, oops, that's not what I want to do. 1920 divide by, so if I do 10 MIP levels here of this thing, so the 1920 is one level, then that's the second level, third level, fourth level, oops. First level, second level, so that's 2, 3, 4, 5, 6, 7, 8, 9, 10. I get down to something that's like 4 pixels wide. And a 4x1 would be fine for our purposes, right? For a minimum level. So we could, pretty trivially do a 4x1. If we wanted to make sure we got down to things that were always no more than 2, we would need 11 MIP maps, right? And if we wanted to always go down to a 1x1, then we would know that we would need 12, right? Because that's the only power of 2 that effectively can encompass the 1920. So it's our choice of how we want to do that, whether we want 10, 11, or 12. I'm not sure. I'm not sure how much it matters exactly. Let's start by saying we're going to use 10, or rather, we might even say let's use 9, because maybe we don't really want to in the circumstance where we would have this always doing a 2x2 effectively, we would want to make sure that we always have 2 in Y. And so 10 MIP levels means that at the lowest level we only have 1 pixel in Y, 1 texel in Y, 1 texel high. And so maybe we don't want that exactly. So I think what I would say is we have our light buffer. In our light buffer here, this stuff goes away. Our light buffers would have no more than 12, right? Light buffer count. And our light buffer is going to be now this very special purpose nutso thing that we are going to have to create relatively special purpose, right? So what does the light buffer have according to what we talked about before? Well, it's got a front emission texture. It's got a back emit, right? It's got a reflectance. I don't know what we want to call this. I guess it's the just the surface color. And then it's got a special texture that's the normal depth, or like it's the NP, let's say. It's the thing that tells us the location plus the normal of the texture, which is a special purpose texture. And so we can just not store the NZ value probably, or maybe we want to store like, NX NZ because, a lot of times our stuff will be heavily pointing in the Z direction, so we want to store the most dominant value, right? So maybe it's NX NZ or something like that, and the depth. So we've got these textures that we're going to store, and these are all 3 elements. So like note, Casey, these are all 3 elements. Would be how we would store these, I guess. But again, we could just decide to pack them and be clever. It seems like we probably should do that. Because why not? Right? I can't think of any reason why we wouldn't do that necessarily. Well, on the way back down, we never write to this, or this. So we're only writing to these 2, right? So it would make a lot more sense probably to treat those as separate and these 2 as separate. So, maybe, yeah, we don't want to merge them. I don't know. Yeah, I think we don't want to merge them because we want to read from these on the way back down and write to these. Potentially. Or other things like that. I mean, I don't know that we actually want to do that, but we might. It's plausible that we could potentially do that. So we want these. And then we've got the frame buffers. So the frame buffers here would be something that writes to the front and back emit surface color texture and the MP text. So this is a write all frame buffer kind of a thing, and that's used for the pass up. And then there's a write emit. Because the write emit is the frame buffer we'd actually use on the way down, because once you've built those MIPs, you no longer need to ask what the surface color or NP texture, I'm sorry, you no longer need to modify what the surface color texture or the normal depth texture is at the levels because it's just known, right? It never gets changed again. It's just emitted light then that you're sort of pushing back around in those cases, right? So it seems to me, at least to a certain extent, that would give me roughly what I want, right? That gives me mostly all I would need. So this is my frame buffer for writing to everything, which gets used on the way up and used also for producing this initial set of values from the depth peeler results. And then the emitter one is just for the down pass, right?
Okay.
So we would need to produce a set of these for, a set of these for use with the MIP stuff, and we need the rather complicated shaders that will be used for that MIPing. But we also need the other part of the process, which is sort of the part that we should get started on now, which is that after we have these light buffers produced, we also need some way of writing to them in the first place. And that's a little trickier than it should be. So let me compile and kind of get rid of some of this stuff here. So what I want to do here is have a thing that frees, let's see here, free frame buffer. So what we want here is something like this. When we delete these light buffers, we've got so we would have something like, okay, we've got a light buffer. It's whatever the light buffers are at this point. So we're going to go through here and say, let's delete each of these parts of it. There we go. So that's how we would delete these, and then we just need some way of actually allocating these, and that would be this saucy gentleman right here. And so we've got a light buffer count here that we're going to want to set. At the moment, I'm just going to set it to 9. Well, actually, no, we'll set it to 10, let's say. We're going to get rid of all of this stuff and the version in the settings. For now. And again, we will add probably some settings for lighting in there later that we'll recreate here. But this is the basic outline of the routine. And again, we're not really going to be able to use any of the stuff that we've written for frame buffers or any of that stuff because this is going to be very specific. These things are going to be different from any of the other things we use frame buffers for because they're going to write to 2 color textures at the same time and all sorts of other nonsense like this. All right. So now what we need to do is actually create these. And we do have basically the outline of what that would look like. So we have a frame buffer text image thing here, which you can see us creating. This is not really what we want, but we're going to want something similar to this. I guess looking at it, we can probably make this work. What's kind of interesting about GL text image 2D is why, if you're not passing anything, do you even have to specify anything here? You know what I'm saying? Like, what's the point of that? They have an updated version called GL Text Storage, which is like way better. It's much better than GL Text Image 2D, but I don't know if all cards support it. I think a lot of Intel stuff doesn't support it, at least not without the like most latest of all late drivers. But it looks like we should be able to use this actually, as long as BGRA-X isn't a problem. In this case, so yeah, and I guess I don't know again. Like, is there some way we could just pass zeros for these, or would it get upset with us? Like, can we just pass 0? Let's find out first of all. Let me just try it, and then we'll see whether that's an anomaly of the card or whether that's actually allowed. Because again, we're not trying to submit anything, so I'm not sure why we would have to specify anything there. We specified the internal storage format. That's all we should need, right? So what if I did that? What if I just said, hey, yeah, we're just not passing anything. Yep, just as I suspected. Invalid, That's really unfortunate, because, like, man, it's just dumb. Like, why would you have to pass something? It's just stupid, because there's nothing happening there. But anyway, oh well. But frame buffer text image is what we could use in this case, right? So if we wanted to here, right, I could sort of crib off of that. And when we do our light buffers and create them, we could still use this function. So we would have the width and the height here. This is just going to be a texture 2D because we're not going to multi-sample these at all. And the internal frame buffer format here is going to probably be a like a 16F or an RGB 16F version. Probably is what we'll want to get away with. And what we'll start with is a 32F and do a note here, Casey. Drop this down to 16F once we know what's what. Because we don't really want to eat all that bandwidth for 32-bit floats when we really probably don't need them for lighting. But when we start, I usually like to start by doing everything in 32-bit floating point since cards allow it. And it helps you know that you're not getting a bug from precision errors or clamping errors. And then that way you can just toggle it down to something smaller later and then know that what you see is a well-working algorithm that just has now been reduced in precision, so you can estimate whether it's worth that reduction in precision, right? So what I want to do here, is do frame buffer text image for a couple different things. So let's say we have our buffer here, and I want to create one of these for each of the things that we've got. And so I've got my front emission texture here. Oops. I've got my back emission texture here. I've got my surface color texture here and my NP text. Now in each of these cases, I would also point out the fact that the surface color since it's just used for the reflection equation, almost certainly could just be stored in sRGB8, right? There's almost no need for it to be 16 per gun, I don't think. The NP text itself probably could also be sort of done in sRGB8. Because again, we don't really need the depth to be exact. And obviously the direction doesn't have to be exact either. So I strongly suspect that we could really cut down on the total number of bytes we're actually dealing with here, because probably it's only emission that's going to need to store something fancier than 8-bit. And even that could probably be encoded in 8-bit. Because if you think about it, it's like, well, you know, how much do we care how accurate the emission is? So let's just say that this number from 0 to 255 ranged actually was like brightness 0 to 10, you know? And yeah, it's not that granular, but who cares? So I don't know. We could probably get away with a lot of stuff there. I don't know. Maybe, maybe not. Honestly, the problem with that is you'd end up with a lot of banding, and that doesn't matter. Anyway, so I would say that we could definitely get this down if we want to. At first, I'm definitely starting with floats, though, because you don't want to introduce extra sort of possible confusion in there about what's going wrong. You want to minimize the number of things that can go wrong when you're working with the GPU, since you can't step through it, at least not on our machine. So here's, I don't know what... This is just texture 2D, correct? Here's how we would attach those. So one of our frame buffers is going to have to attach them all, right? So it would basically be each of these guys, back emit, surface color, and NP. And maybe I should call this just what it is, NX and NZ, or, well, no. Because we might change that encoding, and then we have to change the name everywhere for no reason. So yeah, if I do this, GL frame buffer texture 2D, there's nothing special I have to think about there, I don't think. Because we're only creating one MIP level for any of these. So I think, oops, I think we're fine. So one of them is going to be that, one of them is going to be this. So it depends on which frame buffer we're doing. So this is the down frame buffer, and this is the up frame buffer. So as we sort of build our MIPS, we would be doing writes to all four. As we do our traversal back down to spread the light, we would only be writing to the light. Right. And so then I just need the thing that creates the frame buffer. And so here we would have something like this. Oops. And I would like to keep this like so. And so in here, what we want to do is just say, all right, we've got our buffer. It's the write all buffer. Here it is, right? Then we've got this one. This is the write emitter. And neither of these are going to have a depth buffer because we never want to do depth testing or anything like that. We're just building MIP levels. So as we go, we're just kind of aggregating these things together, right? And I think that's basically it. Oops. Got to restore that to working order. And so here I want to take, and I want to get the light buffer out of there. And now I just need to know what the texture width and height are. So in this case, we've got text width, text height. And for the texture width and texture height, those are just whatever the render width and render height are. And then each time through here, we do a text width divide equal by 2 and a text height divide equal by 2. Right, so they're getting successively smaller, smaller, and smaller. If at any time the text width is less than 1, it should be set to 1. And if the text height is less than 1, it should be set to 1. Because we don't ever want to MIP down below 1 and have a 0, like a 0-dimension texture is not going to work. Right. So it looks like we didn't copy the GL color attachment for the other ones from core arb. So just grab those real quick. Hello, color attachment. There they all are. All right. So now we are creating those surfaces and they're ready to go. And I think we can kind of end now. And tomorrow we can start by trying to build those, which will require two things. First, it will require us to have a way of specifying lights. Right now we don't. And so the way that we'll be doing that is we will have a way for you to specify that something is emissive. And then we will have to start doing the actual work of building those shaders, which will probably take us a couple weekends to get right. And then it'll work or it won't. And we'll either be happy or sad. Dator, are you planning on taking a different non-conventional approach to lighting? Yeah, I would say we're taking a pretty non-conventional approach to lighting, yes. It's a unicorn dog. Any recommended programs to use for a noob? That's a pretty open-ended question. A noob in what? A noob in programming? And when you say any recommended programs, what do you mean? Like editors or compilers or like what do you mean? Is that metal music coming from the stream or am I tripping? I hear nothing outside. Dr. Will you port the game to JAI or make a port of it in JAI once it comes out? No, we won't be porting the game to JAI, just because I don't think JAI will be done. Well, okay, even if it were done today, I'm not gonna, you know, go restart the entire programming process in that language, right? If JAI had been done back when we started, we might have considered just doing it in that language, but that's not really feasible now. I assume probably somebody will port it to JAI because there's people who've done ports to like D and Rust and other things. They get varying degrees of through it. Like, I don't know that people always stick with it that well because they get bored or whatever. But also, when it's all done, it'll probably be easier to do a port because you could just port directly and it's not too hard. So. Will SCH, which do you think will take longer, coding the engine or coding the actual game? Probably coding the engine, but I don't know. That's really more about how much stuff we put in the game. So it's kind of open-ended. We can certainly choose to make coding the game take longer because we can keep adding things to the game. The engine, we don't have much more to add, right? Once we have lighting, and we do some cleanup maybe with like creation and pathfinding stuff, then we're mostly done with anything that we would call strictly engine. So, you know, there's not a lot of strictly engine things we could be doing at this point. You know, we'd have to go start upgrading things like music compression or things, you know, we'd have to like add compression-y stuff or rebuild the software rasterizer at some point. So there's some things we could do that would increase the engine workload, but you know, we've done most of the things. So really, I think mostly what we're looking at now is, okay, you know, how many hours did we spend on engine coding? 400 hours, 500 hours, something like that. And so if we spent like 500 hours on game programming, I'm sorry, if we spent 500 hours on engine programming, that's what? That's, you know, a couple months of full-time programming work, essentially. Not very much for someone to do, you know, certainly achievable. How many months of full-time game programming work do we think should go into this game? You know, probably should be similar, right? 500 hours, I don't know. You can always find more things to put into a game to make it better. And when I say put into a game, I don't usually mean like just adding features or anything, because adding more features doesn't necessarily make a game better. But you could always focus on like, oh, could we tune this part? Could we tune that part? Could we change some item balancing here? Like, you can usually find stuff to spend your time on. So I would suspect that it's going to be largely up to us. It'll really depend on how much stuff we want to put into the game. It's a unicorn dog editor for programming. So if you want to know what an good editor for programming for a new programmer is, I would say just use the one that's built into Visual Studio, right? Because if you're brand new, just cut down on the number of things you have to learn. So just use the editor that's in Visual Studio, assuming you're on Windows, and build and run and edit in one package, right? Simplify. Once you get good enough to care about editing, you may want to consider a more high-powered editor, like 4Coder or something. I use 4Coder, and I like that quite a bit. So, you know, maybe you want something like that where you can customize it in C and make it do a lot more stuff for you. But you don't need to do all of that at once, right? You can start out with just the basics. Holst 80, do you work on Handmade Hero outside the streaming time? No. The hard and fast rule on Handmade Hero is I am never allowed to type a single line of code that you do not watch and I have to explain it. So it is the slowest possible development process you could possibly undertake for a game. I literally type every single change on the stream. I explain it every time on the stream, and I'm not even allowed to think about it overtly outside the stream. So I do no pre-planning whatsoever. The only things that I do outside the stream are when I happen to think of something, when I'm just like walking around doing something else and I'm like, oh, maybe we could use depth peels for lighting. Like, I might just think of something and I can't like stop myself from doing that. But even planning has to occur on the stream, like you saw today where I discussed the lighting and stuff. So Handmade Hero, you see 100% of the development process, period. There is nothing in the game development, other than like the art asset production, right, or whatever, that is not on the stream. So another way to state that is like, if I were to do it myself separately from Handmade Hero, it would take no more than the time that it has taken on stream to do, but actually probably much less, because I wouldn't have to explain anything. Gary Johansson, code blocks was not usable when I last tried programming Linux, which admittedly was 2013. Programming entirely on Linux, 2013, 2014, because it had a bunch of stuff that it couldn't do. I don't remember what they were. It was either like you couldn't view assembly language or step through assembly language, or you couldn't view a memory window, or you couldn't launch a debugger that you didn't build inside code blocks. You couldn't debug an executable you didn't build inside code blocks. I don't remember what they were, but I have like a list of things you got to be able to do to be a usable debugger, and it definitely failed. Now, whether they've added them since then, I don't know. So you might have to recheck. About retained and immediate mode, do you think these paradigm boxes work for game code as opposed to engine code as well? So what I would say about immediate and retained mode is that they really are just ways of conceptualizing an interface boundary, and they work everywhere, right? Like, they're always a lens you can look at to determine how your interface works. Does your interface require the person on either side of the boundary to have a corresponding lifetime management for objects, whatever they are? And I don't really mean object in the object-oriented sense. I just mean any conceptual element that it defines, or does it not? And that's really what retained and immediate mode is. Something has a lot of retention, and I tend to think of it in terms of just the concept of retention. So saying that something's immediate mode is not really a statement about having something in particular. It's a statement about not having something. So when I say that something is immediate mode, what I mean is it has low or no retention. And when I say something's at retained mode, I mean it has high retention. And what retention is retention is the idea, and I don't particularly like this term, I would prefer a different term, but it's unfortunately just what was the original terminology when I got here, right? I was not even probably born at the time when someone invented the term retained mode. I don't know, maybe I was like 10 or something, but what I mean by retention is the degree to which the user on the non-reusable or the non-reused side of the API boundary knows about the lifetime of something on the reused side of the boundary. And I shouldn't say knows about, what I really mean is controls. So, to take a simple example of a button, let's say, since retained mode GUIs are common, let's say I take a API where the user of a library, so we've got the user and the library, there's an API boundary between them. If the user has to create and destroy the button as individual events, then that is a high retention API for that button, because the user has to be in complete control of the existence of the button. This means that the existence of the button is now completely mirrored on both sides of the boundary in a behavioral sense, right? Meaning that the actual event of creating and destroying the button has to exist on both sides of the API boundary. So that's high retention. So a low retention or no retention API is one where whenever the user wants there to be a button, they simply say there is a button to the library. And if they don't say there's a button, then there isn't a button. So now there's no retention. The event of creating the button exists only on the side of the library. And on the user side, they simply know whether they wanted a button or not on any particular time and just ask for that at that time, right? Now these things have pluses and minuses, but most of the time low retention is better. And the reason that low retention is better is because it reduces the degree to which you can have errors in the communication across the API boundary. You know for a fact that the user side has existence criteria that it is maintaining about whether or not there is a button. For example, if the user side wants to show a dialogue, it has to know in its state stuff about where it is in its understanding of what's going on to know that that dialogue had to occur. Now, when that dialogue has to occur, that's the piece of state that actually matters to the user side. So it is tracking the fact that the user is interacting with a dialogue right now. What it doesn't care about is the fact that all the things in the dialogue exist, right? It doesn't want to track that state. If there's 1,000 buttons in the dialog box, I don't want to track that they all exist. I just want to track that the dialog box exists, right? And furthermore, I don't even really want to track that the dialog box exists. What I really wanted to track was that the user is in the mode of interacting with the dialog box. So what then happens is that user, if it's in, oh, I'm in dialog box interaction mode, let me tell the library about these buttons that should be on the screen that should be clickable, right? The library should then be responsible for tracking whether those buttons exist. And when the user stops telling the library that we're in dialog interaction mode, those buttons should just get cleaned up, right? And so typically when you're shipping a library to someone, I kind of think of that as the better way to design it. And I think that that's true across basically everything. If you are talking about an API boundary of reuse, I think to a large extent, you want to really be careful what things you require retention for and which ones you don't. Masielda, if so, would you write your game logic code in immediate mode or retained mode? So the answer is that it depends if you're trying to create an API boundary there or not, right? And so one of the things you'll notice is that we kind of did write our game logic code in immediate mode. If you look at how our game logic code is set up right now, the way that it works is we stream entities in, we edit them, and then we stream them out. What that means is that the game never really updates the main database of where everything is stored. It never really talks about things getting deleted or not, right? What happens is just when we do all of our entity work, if we want to kill an entity, we just say, oh, that entity is dead now. And then when it goes to get stored back, it just won't get stored back. So in a sense, we did write it in a very immediate mode fashion. We don't actually go ask the game database to delete the entity. We assume all entities are deleted until we hear that they are back, right, in a sense. And so I think a lot of that stuff will look very immediate mode. But the point is not to eliminate storing things, because programs are about storing things. The point is that at certain API boundaries, it makes sense for ease of use to eliminate or reduce the number of things that the person on one side of the boundary needs to tell the person on the other side about lifetime. Another way to say it might be, if the lifetime of an object can be implicit in the usage of the API, it should be. Or at least consider it. Because forcing lifetime to be explicit requires you to hold a bunch of unnecessary handles on one side, and it requires you to make a bunch of unnecessary calls to clean things up. I plan on starting a project this summer, a 4D perspective projection voxel game. Okay. May I ask you for some tips on graphics? Like, how do I utilize graphics card the best? Because it's not optimized for 5x5 matrices, and it's hard to think with other concepts for me. I wouldn't get too worried about the fact that it's not optimized for 5x5 matrices, because it actually is optimized for 5x5 matrices, is maybe what I'd say. There's probably some inefficiencies there, but let me just remind everyone, and I think I talked about this a long time ago, but GPUs aren't actually X, Y, Z, W vectors. So you will oftentimes see stuff on the GPU that's like, you know, vec4 p, mat4, I don't remember what the name of it is, because we use our own type defs for these. Mat4, you know, matrix, and then you'll see like vec4, you know, transformed point equals mat times p, right? So you'll see that in a shader, and you'll think to yourself, oh, well, clearly we've got all these vec4 things. Obviously, the GPU's ALU is like super optimized for like doing these like 4x4 matrix multiplies, and I'm totally screwed if I go to 5x5. The answer is not probably the case. If you're on like an NVIDIA card or something like that, a modern graphics card, it's just probably not the case. Why is it not the case? Well, it's not the case because you see a lot of stuff that's like, oh, you know, color.rg, you know, access just the red and green components of something, or replicate the R component out to a bunch of things, like, you know, this color value equals the red replicated. So a lot of the stuff that graphics cards do in shaders, a lot of the code that they have to handle works out of sub-elements of these vectors, right? As a result, graphics card design right now is not about vectors stored as packed XYZ. That's not how they work. Similarly, typically they're working on arrays of like 4x4 pixels or stuff like this, which again would not fit into vec4s very conveniently if you don't know what these are. If these could be like depth components or whatever, right? Blah, blah, blah. So typically what graphics cards actually are is they're wide versions of the scalar path. So typically what happens if this is a vector shade, if this is a vertex shader, typically what happens is it's not running a 4-element wide version of this shader on one vertex. What it's doing is running 16 vertices in parallel through the same shader in a scalar path. So the first thing that happens in the shader compiler is this gets blown out to the full matrix multiply scalar, right? So it's like mat, you know, 0, 0 dot p0 plus mat 0, 1 times p, right? It blows out the full scalar version, and then it does it for 16 vertices at a time, as if each vertex was done in scalar, vertex done in scalar. So if you want to write a 5x5 matrix multiply, go right ahead. It should pretty much run at the same speed. And maybe there are some very specific things in some cases where you'll get a slight slowdown there, but it is absolutely not a problem to think about a vertex shader as scalar and run it that way. Does that help? And really the only thing that like thinking it through, the only thing I can think of that you might run into, and again, I'm not an expert on this, so take it with a grain of salt, but I think the ALU path, like all the arithmetic, I think you're just fine. You'll run at full speed. The only thing I think you might be aware of is I don't know to what extent the memory unpack is based around XYZ, XYZW. So some of like the memory unpacking might be less good because in order to get those 5-element things out into the right places, maybe they won't, you know, so, but that's it. So I think it's just memory unpack is about the only thing that might downshift you at all. But your ALU speed should be fine. I think. All right. Oops, you know what? Since it was so hard to find this thing, I'm going to leave that open. All right. Thank you, everyone, for joining me for an episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with a source code so that you can try it yourself and play around with it. We also have a forum site you can go to if you want to support the video series, a Patreon page you can go to, a forum site you can go to if you want to ask questions, a Patreon page you can go to if you want to support the video series, a schedule bot that tweets the schedule so you know when we're going to be live if you want to catch us live, and an episode guide that you can use to catch up on past episodes. That's about it for today. I will be back tomorrow with more Handmade Hero lighting coding, where we'll try to get some of those light buffers filled up. We won't get to actual lighting tomorrow because just getting the lighting buffers filled properly and MIPing properly will definitely take a full 2 hours, probably more, but we will get it started. And then next weekend, we'll see if we can get some actual lighting working. That's about it. I hope to see you back here tomorrow for that. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.